When you think of a machine, a robot, or a mechanism, you likely think of a collection of rigid bodies that work together to achieve a desired task, which, in the case of this Janssen linkage, is locomotion. But when you consider the machines that nature designs, you probably don't think of clunky, rigid bodies connected together by well-defined joints. Plants and animals tend to be soft, bendable, and flexible, and they use this compliance to achieve tasks that are far more advanced than even the most impressive machines that humans have designed. True, some of the rigid machines that humans have designed have managed to outperform nature's compliant machines, like this jet that can fly much faster than any living creature can. But no one denies that nature's flying machines are masterpieces of design that are far more maneuverable, agile, and energy efficient than any aircraft humans have ever built. In fact, designs that are compliant are advantageous for many reasons. Sorry, where was I? Oh yes, the advantages of compliant designs. Well, they are repeatable, scalable, human-safe, adaptable, lightweight, lower cost, easier to maintain, easier to fabricate, friction-free, hysteresis-free, more robust, passively deployable, easier to exactly constrain, easier to not under-constrain, easier to achieve symmetry, more accurate, soft, electricity-free, and more energy efficient. They minimize part count, require minimal or no assembly, accommodate imperfections, and the list goes on and on and on. So it begs the question, if the benefits of compliance are so numerous and significant, and if nature has predominantly selected for compliance over rigidity after billions of years of constant design iteration, why don't we design more machines that are compliant? Well, because compliant machines are harder to design than rigid machines. Hi, I'm Jonathan Hopkins. I'm a professor of mechanical engineering and am the director of the Flexible Research Group at UCLA. I dedicated my career to making the design of compliant mechanisms easier because I believe some of the most exciting future technologies will be enabled by compliance, and my goal is to help bring about the creation of those technologies. In this course, I'm going to teach you how to design compliant mechanisms using the most popular and advanced design approaches created to date. Specifically, I'm going to focus on teaching a design approach that I created as a graduate student at MIT in 2005 and have been advancing ever since. The approach is called Freedom and Constraint Topologies, or FACT, and is the namesake for this YouTube channel. FACT is an active area of research and is currently taught in undergraduate and graduate level courses in universities worldwide. It's attracted numerous awards and is the reason I was honored by President Barack Obama at the White House in 2016 with a Presidential Early Career Award. In this course, I'm going to demonstrate how FACT can be used to quickly search the complete design space of compliant mechanisms embodied by the geometric shapes of this library. I'll show you how you can use these geometric shapes to rapidly identify the most promising topology solutions, and how you can then optimize the geometry of those solutions using complementary approaches. I'll discuss tips about how your final optimized designs can most successfully be made and assembled, and will provide you the tools that are necessary for you to know how best to actuate or push on them so they deform the way you intended. If you don't like math, don't worry. You won't need to know any math to understand the core episodes. If you do like math, you're in luck, since I will provide extra math lectures to supplement the core episodes so you can delve as deep into the theory as you like. But trust me, these math lectures aren't necessary to understand and apply the design principles of this course. If you are interested in precision flexure systems, soft robots, MEMS devices, origami, or really any mechanism that deforms to achieve an interesting task, this course is for you. Perhaps you want to transform an existing rigid mechanism into an improved compliant version of the same mechanism. Or you want to create a transmission mechanism that transforms one motion into other motions at different locations and in different directions, like this compliant gripper. Or perhaps you want to constrain a motion stage so that it can deform with high compliance in certain directions while remaining stiff in all other directions. Whatever your objective, I promise that if you internalize the content of these episodes and do the suggested assignments, you will not only become a master of compliant mechanism design, but the way you view the world around you will never be the same again. So buckle your compliant seatbelts. How you approach mechanical design is about to become a lot more flexible. Thanks for watching The Facts of Mechanical Design. I hope you enjoyed part 1 of my compliant mechanism design course. Parts 2 through 8 expound on the importance of compliant mechanisms in the context of relevant fundamental principles and common everyday examples. If you're already sold on the importance of compliant mechanisms and you're watching this course solely to learn how to design them, feel free to skip to part 9 and you won't miss out on any critical content necessary to understand and apply the rest of the course's material. Otherwise, continue on to part 2 and enjoy. Also, be sure to check out my website to access free online resources that supplement this course with optional reading materials, assignments, and practice problems. The link to the website is in the description below. Thanks again for watching.